Hey everyone. We all have so many devices that use batteries and particularly rechargeable batteries that I thought it would be a good idea to make a short video. I'll make it as short as possible and explain to you the very, very basics of how our battery devices work and what that has to do with circuits and potential energy. Let's start with a quick definition. A battery is simply a device that converts chemical energy into electrical energy. So batteries store chemical energy. That's important. This is done by transferring electrons. The way we convert chemical energy into electrical energy is to transfer electrons from one material to another through an electric circuit. This results in the oxidation of a reducing agent on the anode and the reduction of an oxidizer on the cathode. And this is called an oxidation reduction or redox reaction. And you guys may remember that from your chemistry days. The term oxidation means that the material is losing electrons, and the term reduction means that the material is gaining electrons. You may remember that Leo goes Ger. When you lose electrons, it's oxidizing, so Leo goes Ger, and you gain electrons. That's reduction. All right, let's take a quick look at the inside of a battery. Batteries has some basic components. All batteries have an anode and a cathode. They all have some type of electrolyte material on the inside, and there has to be some separator that allows the flow of ions but keeps the anode and the cathode separated. I won't go into too much detail here except to say there's a chemical reaction that occurs inside the battery as we discharge it. So this chemical reaction occurs and electrons flow through the external circuit, and once this chemical reaction is depleted, that's when your battery's dead. To charge the battery, you have to get some energy from an outside source. So when you plug it into the wall, you add energy back into the battery, and what it does is it undoes this chemical reaction and returns things to their original state so that the chemical reaction can occur all over again. So charging a battery, you're just undoing the chemical reaction. All right, now get into a couple of things that are really relevant to what we're doing. There's an internal circuit inside a battery, and then the external circuit we think about. And we always use a positive test charge, if you remember in our previous video. So if you have a positive test charge inside a battery that has been discharged, well, if you think about it, those positive and negatives are attracted to each other. And the only way that you get the positives piled up here on this other end is you have to do work. So in the internal circuit of a battery, so in the internal circuit, or let me put it up here on the top. In the internal circuit, a positive charge gains potential energy. All right, because as you push that positive test charge up here, you have to do work on this charge in the internal circuit for it to gain potential energy. And then when you complete the external circuit, this on the outside, out here, you have this positive test charge now that will flow freely and do some work here as it goes back to this low potential energy state. So in the external circuit, a positive test charge will lose potential energy. All right, and so the loss on the outside equals the gain on the inside, and then we have that conservation of energy thing going on again. All right, so one last quick thing. Let's take a look at an analogy that I think helps a lot of folks when we think about this. So we've always used this an analogy of gravitational potential energy. So if we have a battery, say, that's got 4.5 volts marked on it, well, what does that mean? Remember, we did some work on the inside. So over here, let's say we had a ball, and we lift it up to the top of a set of stairs or something. You have to do work. You have to multiply. We use a force through a distance to move this object up here. And now there's some gravitational potential energy at the top. And if you think about it, if this is A and B across the top of the stairs, if the ball moves from A to B, there's no change in potential energy. But if it moves from B to C and this ball goes down, then here there's a loss of energy, a loss of potential energy. If this corner of the stairs here from C to D, if the ball moves level across there, the potential energy doesn't change. If it goes from D to E, then again there would be another loss of gravitational potential energy as that ball moves to the next stair. From E to F there would be no change, and then from F to G, you can guess it, as the ball goes down there, there'd be another loss of energy. And so what would that have to do with an electric circuit? I'm going to move this over a little bit, give myself some room. Well, let's say we've got 3 losses here, so let's have 3 items over here that use energy. Let's put three light bulbs in here. I'm trying to draw quickly, and let's see what would happen. How this matches the idea. Well, we have 4.5 volts of potential here at A, and as we go to B, there would be no voltage loss across here, so we'd have 4.5 volts available. But as we go from B to C, that's the same as this drop over here in the waterfall. From B to C, since there's 3 atoms here, we would lose 1.5 volts, which means at C, we'd only have 3 volts available to us. Move from C to D, there'd be no change. But then as we go through the bulb from D to E, be the same business we had over here. That's when you drop down this stair step, we lose some more. So if we used another 1.5 volts, we'd have 1.5 volts available as we got through there. E to F, there'd be no change. All right, but then as we go from F to G, as we go through this last bot bulb, we would use another 1.5 volts, so that by the time we got to G over here, we'd be at 0 volts, and that's the same thing we see over here in this gravitational potential example. So the analogy really holds true because we're talking about potential energies. Over here we lose potential energy as we go down a step, and in a circuit we lose potential energy as we go through some device that requires energy, like a light bulb or a resistor or some other, a motor or some other thing. And so anyway, I hope that helps you understand batteries just a little bit. I didn't want to make this video too long, so I'm going to stop here, and I'll see you guys later.